Okay, so organic chemistry, it can feel a little overwhelming sometimes, right?
It's true.
Like, where do you even begin?
Yeah,
But here's the thing. There are these patterns,
exactly.
these kind of VIPs in the molecular world,
And those are,
functional groups.
of course.
Once you learn to recognize them,
It's like,
it's like that aha moment.
yes.
Things start to click,
Exactly. It's like having a cheat sheet for understanding how molecules behave.
which is what we're all about today, right?
Absolutely.
We're doing a deep dive into, you got to know these functional groups.
A deep dive. I like it.
Trying to cut through all that dense textbook stuff
Right.
and really just extract, the gold, the important things that we need to remember,
The essentials.
the essentials. So, are you ready to get started?
I'm ready.
All right. Let's start with the basics. Hydrocarbons.
Okay.
Got our alkenes, our alkenes, and our alkynes. Can you break those down for us?
Sure. So think of them as the foundation, right? The simplest organic compounds composed of only carbon and hydrogen,
Okay.
and the key difference between them.
Let me guess. It's all about those bonds, isn't it?
You got it.
Yeah.
You're exactly right. It's all about the type of carbon bonds. Alkenes, they're like that friend who always plays it safe. They only have single bonds, very stable, not very reactive.
Okay.
But alkenes, on the other hand, they like to live a little. They have at least one double bond, which makes them a bit more reactive. And then we've got the alkenes. They're the wild ones, always up for anything, with at least one triple bond, a lot of energy packed into those triple bonds.
And the text makes this cool comparison between alkanes and alkenes, and something I think a lot of us are familiar with, which is fats.
Oh, absolutely.
We can talk a little bit about that.
Yeah. So just like we were talking about single versus double bonds, right? You've got your saturated and unsaturated fats.
Okay.
So saturated fats, those are your alkenes. Think butter, solid at room temperature, all those single bonds, nice and packed together.
Uh-huh.
But unsaturated fats, those are your alkenes. Think olive oil, liquid at room temperature.
Right.
Those double bonds creating kinks in the structure, so they don't pack together as tightly.
That actually makes a lot of sense. It's a great way to visualize it.
Yeah.
Now, the text also mentions a couple of specific examples of alkenes and alkenes, ethylene and acetylene. What makes them so special?
Oh, they're fascinating. So ethylene, for example, it's a plant hormone,
Oh, interesting.
a ripening agent. It's actually why if you put, say, an unripe avocado in a bag with a banana,
Oh, yeah.
that banana is releasing ethylene gas, and boom, ripe avocado in a couple of days.
It works like a charm.
It really does.
I use that trick all the time.
It's handy. And acetylene, on the other hand, that's used as a fuel in welding because that triple bond stores a ton of energy, burns really hot and fast.
Interesting. So from ripening fruit to, welding metal, it's all thanks to those alkenes and alkenes.
It's incredible, right?
It is. Okay.
Yeah.
Let's move on from our building blocks, our hydrocarbons, to something a bit more, shall we say, potent.
Ooh. Talk about alcohols.
Alcohols, they're a fun group. They are fun, and they get a lot of attention, and not just for their role in,
Right, exactly.
beverages.
They're more than just a cocktail ingredient.
So what defines an alcohol?
Well, it all comes down to that hydroxyl group.
Okay,
So we're talking about an oxygen atom bonded to a hydrogen atom, that's your OH.
gotcha.
And that OH group, it's directly attached to a carbon atom. So whether you've got methanol, ethanol, isopropanol, they all share that OH in common.
It's like their little club membership card.
Exactly, their molecular ID.
And, of course, the text points out that even a small change in that molecular structure can have a huge effect on the outcome.
Oh, absolutely.
Like methanol, super toxic.
Dangerously toxic.
Ethanol, but that's what gives us a certain kind of spirit.
Right, it's all about those slight variations in structure.
Yeah. And it's not just about those single hydroxyl groups. You've got diols, trials. Things can get even more interesting.
Oh, for sure, the party's just getting started.
So let's talk about those.
Let's. So diols, those have 2 hydroxyl groups in trials. They're rocking 3. And that's where things get really interesting.
Okay, like what? Give me an example.
Take ethylene glycol.
Yep.
It's a diol. And it's the main ingredient in antifreeze.
Really? Antifreeze. Who knew?
Because it helps regulate those freezing and boiling points.
That's pretty important.
Keeps your car happy.
What about glycerol? That was mentioned in the text as well.
Glycerol, that one's a trial. And it's the backbone of triglycerides,
Okay.
which are a type of fat found in our bodies in food.
Wow.
So from preventing your car from freezing to storing energy, it's all connected.
It's incredible. Okay, so we've talked about hydrocarbons, we've talked about alcohols. Let's move on to something a little bit more, shall we say, edgy.
Okay, I like where this is going.
Let's talk about alkyl halides.
Alkyl halides. Now we're getting to the good stuff.
A little bit dangerous.
Just a little. So essentially what we have here, you've got your basic hydrocarbon structure.
Okay.
But one or more hydrogen atoms, they've decided to, step aside.
They're out of there.
They're replaced by a halogen.
Okay, so remind me, halogens are?
Fluorine, chlorine, bromine, or iodine.
Gotcha. So it's like they've got this wild card up their sleeve now.
Exactly. They're unpredictable, and those halogens, they like to make things interesting.
How so?
Well, they bring a lot of electronegativity to the table.
Okay, break that down for me. Electronegativity means?
It means they have a strong attraction for electrons.
Ah, so they're playing tug of war with those electrons.
Exactly. And that tug of war, that's where things get interesting. It creates a polar bond,
Okay.
which means that carbon atom, it becomes a little electron deficient.
Electron deficient, meaning
It's lacking some electrons. We call it an electrophile.
an electrophile. It sounds a little bit shady.
Well, they can be pretty reactive, that's for sure, because they're always on the lookout for more electrons. And anything with a bit of extra electron density,
Yeah.
we call those nucleophiles.
Nucleophile.
Nucleophiles.
So it's like this constant dance.
Yeah.
Right? Electrophiles looking for nucleophiles, trying to fill that void.
The molecular tango.
I love it.
Yeah.
And alkyl halides are often right in the middle of it all.
Oh, yeah, they're stirring the pot, causing all sorts of reactions.
And this is actually what made CFC so problematic, right?
Yes. CFCs, chlorofluorocarbons.
Not exactly a household name, but
They were everywhere. In refrigerants, aerosol sprays, all sorts of things.
but then they
It turned out to be a bit of a problem.
Yeah, those ozone layer issues.
See, they were very stable, which seemed like a good thing at the time, non-toxic. But those same properties, they allowed CFCs to reach the upper atmosphere. And those
Right.
chlorine atoms, once they were up there, energized by UV radiation, they started reacting with the ozone layer, depleting it.
And the ozone layer, that's what protects us from all that harmful radiation from the sun.
Exactly.
Not good.
Not good at all.
And the text mentions PFAS as well.
Oh, PFAS. Those are troubles.
Forever chemicals, right?
Another class of alkyl halides.
And they're everywhere too, right?
Nonstick cookware, firefighting foam, you name it. And the problem is those carbon-fluorine bonds,
Yeah.
they are tough to break. So they don't break down easily in the environment.
Which is how they end up everywhere.
Precisely.
It's kind of mind-blowing when you think about it. These tiny little molecules
I know.
causing all these huge problems.
It really puts things in perspective.
It does. It really does.
Mhm.
Okay, let's move from the slightly terrifying to something a little bit lighter.
Okay.
Let's talk about ethers.
Ethers. Now, those are a bit more laid back.
Less reactive, right?
Yeah, think of them as the less dramatic cousins of alcohols.
Okay. So what makes an ether an ether?
Well, picture this. You've got your oxygen atom,
Okay.
and it's feeling a little social.
It wants to make some friends.
Exactly. So instead of just bonding with a carbon and a hydrogen like in an alcohol,
It branches out.
it bonds with two carbon atoms.
Oh, so it's like the oxygen's playing matchmaker.
I liked that. The ultimate wingman.
And that changes things up quite a bit.
It does. Makes them much less reactive than alcohols.
Hence the laid-back label.
Precisely. And that makes them really useful as solvents.
Ah, so they can hang out with other molecules without causing too much drama.
Exactly.
Like diethyl ether that was mentioned in the text.
Ah, diethyl ether. That one has a colorful past.
Tell me more.
One of the first chemicals used for anesthesia.
Really? To put people to sleep for surgery?
Back in the day, yeah.
Wow. I wouldn't want to be the first person to try that out.
Probably not a good idea to experiment with that one at home.
Definitely not. So, from solvents to anesthetics, ethers have quite the resume.
They get around.
They do. Okay, let's move on to another group that definitely gets a lot of attention, although maybe not always for the right reasons.
I think I know where you're going with this.
Let's talk about amines.
Amines. Often misunderstood, but so important.
They are, but they do have a bit of a reputation, don't they?
Well, they're not exactly known for their pleasant aroma.
Yeah, the text mentioned a certain fishy smell.
Yeah, that's a common association.
So what's going on there? What makes amines so pungent?
Well, it all comes down to their structure.
Okay.
Amines have a nitrogen atom,
All right.
and that nitrogen, it's bonded to one or more carbon atoms,
Okay.
often with a lone pair of electrons.
Lone pair of electrons, meaning...
Two electrons that aren't involved in bonding. And those lone pairs, they make amines basic.
Basic, as in?
As in the opposite of acidic.
Yeah.
They can accept protons.
Okay, so on the pH scale, they'd be...
Higher than 7.
Gotcha. So those fishy smells, is that those lone pairs of electrons doing their thing?
Indirectly, it's actually the volatile amines that are usually responsible for those less than pleasant odors.
Volatile amine.
Those are the small, lightweight amines that evaporate easily.
They float around in the air and...
They find their way to our noses.
And we're like, whoa, what's that smell?
Pretty much. But don't let the smell fool you. Amines are incredibly important.
Okay, good. Because I was about to swear them off forever.
They're essential for life, especially in biological systems.
Okay, like how...
Or a key part of amino acids.
Which are?
The building blocks of proteins.
Right.
And they're important in neurotransmission, helping carry those signals throughout our brains and bodies.
So from like fishy smells to brain function, it's all thanks to amines.
It's a wild world.
It is. Okay. We've covered a lot of ground here, but we are not done yet. We still have a few more groups to explore. What's up next?
Let's talk about carbonyls.
Carbonyls. They sound a bit more glamorous, don't they?
A bit, yeah.
What makes a carbonyl a carbonyl?
Well, at their heart, you have a carbon atom double bonded to an oxygen atom.
Okay, so we're back to those double bonds.
Double the trouble.
So what's special about that?
Well, that double bond is where all the action happens, because oxygen is more electronegative than carbon, right?
Right.
So it pulls those electrons towards itself, creating what we call a dipole moment.
A dipole moment.
Yeah, it's like a separation of charge.
Okay.
You've got a partial positive charge on the carbon, partial negative charge on the oxygen.
Gotcha.
And that makes the carbonyl carbon an electrophile.
Oh, there's that word again. So it's still looking for those electrons to fill that void.
Always. They're like the social butterflies of the molecular world, always ready to mingle.
And the text mentions aldehydes and ketones as examples of carbonyls.
Right. Two big players in the carbonyl world.
So how can we tell them apart?
Well, aldehydes, they like to live on the edge. Their carbonyl group is always at the end of a carbon chain.
Okay.
Whereas ketones, they're more middle of the road. Their carbonyl group is somewhere in the middle of a carbon chain.
So location, location, location. It's all about real estate.
In a way, yeah.
What are some examples of aldehydes and ketones?
Well, formaldehyde, ever heard of that one?
Yeah, it's used to preserve, like, biological specimens, right?
Exactly, that's your aldehyde. And then there's acetone.
Acetone. Oh, like nail polish remover.
Flingo. Ketone.
So from preserving tissues to, like, taking off nail polish, it's all thanks to these carbonyls.
Pretty much.
They really are everywhere.
They are versatile, I'll give them that.
Yeah.
And that reactivity, it's why they're so important in forming bigger, more complex molecules.
Like how?
Well, remember esters.
Yeah, those are the ones that give us those fruity smells, right?
Exactly. And they're formed through a reaction between a carboxylic acid,
Carboxylic acid, okay.
which has a carbonyl group, and an alcohol.
Ah, so we're back to those alcohols again.
It's all connected.
It really is. It's amazing how it all comes together. So we were talking about carboxylic acids, and you said they have a carbonyl group.
They do.
So what makes them different from, say, aldehydes or ketones?
Well, they've got that carbonyl group, but they take it to the next level.
Okay, how so?
They add a hydroxyl group,
Okay, that OH group we were talking about before.
the one and only, and they add it directly to that carbonyl carbon.
So they're kind of like a hybrid.
In a way, yeah. And that creates something called a carboxyl group.
Carboxyl group.
That's their claim to fame. It's what gives carboxylic acids their name and their unique personality.
And the text described carboxylic acids as being more oxidized.
Ah, yes, oxidation.
What does that actually mean?
It essentially means that they have a higher ratio of oxygen to carbon
Okay.
compared to, say, aldehydes or ketones.
So more oxygen, more oxidation.
You got it. And that makes them more reactive in certain ways.
Like how?
Well, they're much better at donating that acidic hydrogen.
Acidic hydrogen. Wait, so does that mean that carboxylic acids are acidic?
You're catching on. That hydrogen atom that's attached to the oxygen in that carboxyl group, it can be easily donated as a proton, which increases the concentration of H ions in a solution.
And that's what makes something acidic.
Exactly.
Wow. So when we taste, like, the sourness of vinegar,
Yep.
that's actually the acetic acid, a carboxylic acid doing its thing.
Exactly. Or that tiny citrus flavor, citric acid, another carboxylic acid at work.
Amazing. It's like a whole new world opens up when you understand the chemistry behind it. Okay, we've got just a couple more functional groups to go. What about those aromatic compounds? They sound intriguing.
Aromatic compounds. Now, these are a fascinating bunch. They're all about those ring structures.
Ring structures, okay.
And they have a special kind of bonding that makes them super stable.
Stable as in
They don't react easily.
They're happy just as they are.
Exactly. The most famous example, benzene.
Benzene, yeah. I vaguely remember that from chemistry class. Can you, refresh my memory on what benzene looks like?
Sure. So imagine 6 carbon atoms.
Okay, 6 carbon atoms.
And they're all holding hands, forming a hexagon.
A hexagon.
Each carbon atom also has a hydrogen atom attached to it.
Right.
But here's the thing. Those carbon atoms, they're not just sharing one pair of electrons with each other. They're sharing 3.
Whoa, a 3-way handshake.
It's a party. And those electrons, they form this cloud. It's called a delocalized pi electron cloud, and it spreads out over the entire ring.
A delocalized pi electron cloud. It sounds almost magical.
It's definitely more complex than some of the other bonds we've talked about, but the main takeaway, this delocalization makes benzene incredibly stable.
Because?
Because those electrons are content. They're just buzzing around, happy as can be.
I love it. They found their happy place. And the text mentions something called Huckel's rule.
Ah, yes, Huckel's rule. It's a way to determine whether a ring-shaped molecule is aromatic.
Aromatic, okay. So how does it work?
Essentially, it says that to be aromatic, a ring has to have a certain number of those delocalized pi electrons.
Okay, and how many is that?
It's always a multiple of 4 plus 2.
Multiple of 4 plus 2.
So, benzene, 6 pi electrons, 4 plus 2, it fits.
So it's like an exclusive club and only certain rings get to be a part of it.
Exactly. And membership has its privileges. Aromatic compounds often have very distinct aromas.
Okay, like what?
Think vanilla,
Oh, yeah.
cinnamon. Those aromas, they're influenced by aromatic compounds.
So from the stability of benzene to the enticing aroma of spices, it's all thanks to this unique aromatic structure.
It's pretty amazing. You know, we spent a lot of time talking about the structures of these functional groups, but what's really cool is how they dictate how molecules interact with each other.
Yeah, they're like the rule makers of the molecular world.
Exactly.
They determine who can come to the party and who can't.
And what happens at the party?
It's all about those functional groups. All right, so we're in the home stretch now of our functional group journey.
We are
We made it.
almost there.
We've covered hydrocarbons, alcohols, alkyl halides, ethers, amines.
Quite the lineup.
It's like we've met the whole molecular family.
We're getting there.
So what's next? Who else is left to meet?
Well, no molecular family reunion would be complete without the carbonyls.
Carbonyls. Okay. They sound kind of important.
Oh, they are. They're like the stars of the show when it comes to chemical reactions.
Right. So give me the rundown. What makes a carbonyl a carbonyl?
Okay, so picture this. You have a carbon atom, and it's double bonded to an oxygen atom.
Okay, double bond. We've seen those before.
Right, but this double bond, it's special. It creates a kind of tension.
Tension. How so?
Well, oxygen, it's more electronegative than carbon. It means oxygen really hogs those electrons in the bond. So you end up with this separation of charge, a partial positive charge on the carbon, and a partial negative on the oxygen.
So it's like a tug of war and oxygen's winning.
Basically. And that, my friend, is what we call a dipole moment.
Dipole moment. Okay, I'm getting a little deja vu here. This sounds familiar.
It does, right? It's similar to what we were talking about with alkyl halides and those polar bonds.
Right, where the carbon's looking for electrons to fill that void.
Exactly, and that's what makes carbonyls so reactive, that carbon is always on the lookout for some electrons to even things out.
So they're kind of desperate.
Maybe a little, they just really love to react.
Gotcha. So the text mentioned aldehydes and ketones as examples of carbonyls.
Ah, yes. Aldehydes and ketones, 2 classic carbonyls.
So what's the difference?
Think of it this way. Aldehydes, they're kind of like those folks who always have to be at the front of the line.
Okay.
Their carbonyl group, it's always at the end of a carbon chain.
They like to be seen.
Exactly. While ketones, they're more go with the flow. Their carbonyl group can be anywhere in the middle of a carbon chain.
So it's all about the location of that carbonyl group.
You got it. Location is everything in the world of molecules.
Makes sense. Can you give me some real-world examples of these aldehydes and ketones?
Sure. Thing I've ever heard of formaldehyde.
Formaldehyde, yeah. Isn't that used to preserve stuff?
You got it. That's your aldehyde, keeping things preserved and in tip-top shape, even after,
Right. Not exactly a party trick.
Not unless you're into taxidermy.
What about ketones? Any familiar examples there?
How about acetone?
Acetone, wait a minute, like nail polish remover?
The one and only a classic ketone in action.
Wow. So from preserving specimens to removing nail polish, it's all thanks to these carbonyls.
See, they're pretty versatile.
They are. All right, so we've talked about aldehydes and ketones, but the text also mentioned carboxylic acids.
Yes. Carboxylic acids, the overachievers of the carbonyl family.
Overachievers. How so?
Well, they've got that carbonyl group, but they're not content with just that.
They always had a one-up, isn't it?
Exactly. They go ahead and add a hydroxyl group directly to that carbonyl carbon.
Okay, so they're like a hybrid carbonyl.
You could say that, and that little addition, that hydroxyl group, it creates a whole new functional group called a carboxyl group.
Carboxyl group. So that's what makes a carboxylic acid. Carboxylic acid.
Precisely, that carboxyl group. It's what gives them their unique set of characteristics.
Interesting. And the text mentioned something about carboxylic acids being more oxidized.
Right, oxidation.
What does that even mean in this context?
Good question. Essentially, it means that compared to aldehydes or ketones, carboxylic acids, they have a higher ratio of oxygen atoms to carbon atoms.
So more oxidation?
Yeah, it's all about that oxygen.
And what does that mean for their behavior? Do they get more reactive?
In a way, they become more willing to donate a proton that's that positively charged hydrogen ion we talked about earlier.
Right, and donating a proton makes something more
Acidic.
acidic. Of course, carboxylic acids, acids make sense.
It does, right. And that's why things like vinegar taste sour. It's that acetic acid, carboxylic acid at work.
Wow, so the next time I'm making a salad dressing, I can impress my friends with my carboxylic acid knowledge.
Exactly. You'll be the life of the party.
I can't wait. All right, we've covered a lot of functional groups here, but we're not quite done yet. There are two more groups mentioned in the text that we haven't talked about yet, amides and nitriles.
Ah, yes. Amides and nitriles, they're kind of like the cousins of carboxylic acids.
Okay, how so?
Well, they both contain a nitrogen atom, but in different arrangements. Amides have a nitrogen atom directly bonded to a carbonyl carbon, while nitriles have a nitrogen atom triple bonded to a carbon atom.
Triple bond. Wow, so they're like the super strong silent types?
Exactly, and these unique structures give them their own special properties and reactivity. Amides, for example, are found in the backbone of proteins, forming strong peptide bonds that hold those long chains of amino acids together.
That's pretty important.
Absolutely, and nitriles, with their strong triple bond, are used in all sorts of industrial applications, like making synthetic fibers and plastics.
Wow, so from the building blocks of life to the materials we use every day, it all comes back to these functional groups.
It really does. Chemistry is everywhere once you know where to look.
This has been an incredible journey through the world of molecules.
It has. We've covered so much ground, from those basic hydrocarbons to these complex functional groups.
I feel like I have a whole new understanding of how organic chemistry works.
Me too.
Mm-hmm.
It's amazing how these tiny building blocks can create such a vast and diverse array of molecules.
It really is mind-boggling, and the best part is we've only just scratched the surface.
Exactly. There's always more to learn, more to explore in the world of chemistry.
That's what makes it so exciting. So that's it for this deep dive into the fascinating world of functional groups.
Until next time.
Keep exploring, and we'll see you next time.